Hello, welcome to our Industrial Ventilation EOHS 626 voluntary online review session, April 2nd, 2017. I'm going to go through the assignments, starting with the first assignment, second assignment, and I'll be recording the third assignment, but not discussing it now. As we go through this, this session will serve as an answer sheet for assignment one if we get through it, assignment two as well. And I think that's a good compromise between those of you that want the feedback from how the questions should be answered, and those of you that would prefer to be able to submit them, submit them later on for higher grade. Since we're doing this, even if it's a multiple choice question, when you do your submission, I'm going to ask you to actually show your work in doing the calculations. For instance, question one is multiple choice. We're going to see this problem with that particular one you guys know about already, which is none of the selections is correct. But so you would have to answer that separately anyway. But in question one, question two, instead of just choosing a letter, that you actually show me the work and the calculation. That way it'll encourage you to actually do the submission as if you didn't have this kind of preparation. Okay, so at any rate, hopefully that satisfies the best, it gives us the best of both worlds in any case. Okay, so one of the things I wanted to mention is that just starting right off the bat, that we really want to remember that there's a couple of really important equations that are going to cut across all of the stuff that we're going to do. Okay, and one of those is equal to the relationship between the volume of air that's moving through a ductwork system, the velocity it's moving at, and the cross-sectional area of that ductwork. We know that's Q, which is the quantity of air, is equal to the velocity times the cross-sectional area of the ductwork. In other words, if it's a square duct, right, and something like, say something like this, right? The cross-sectional area is this 1 foot by 2 foot or whatever it is. That's our cross-sectional area. The velocity of air is the speed in feet per minute that it's going through that ductwork. And the volume, Q, right? Q is equal to the quantity of air that's passing that point. That's going to be in feet cubed per minute, cubic feet per minute. Feet per minute, cubic feet per minute. Cross-sectional area, of course, is square feet. Okay, so we have feet per minute times square feet gives us our cubic feet per minute. Okay, and we're working in U.S. system. Okay, we know that there's many tragic situations that have brought up between the conversion, improper conversion between U.S. and metric, and for some reason, even though we had a big push in the 70s that the entire United States was going to convert to metric, and they even put up road signs in kilometers per hour and so on and so forth, it just never seemed to, really take. So we're still stuck with this kind of archaic non-decimal system. Okay, so we're going to stick with that as much as possible because, for the most part, when you order equipment, when you size ductwork, so on and so forth in the United States, you'll be working in those units. Okay, so keep that in mind. The other thing we want to remember is that total pressure is going to be defined as the total of the static pressure plus the velocity pressure. Static pressure is the pressure that's being sucked into the ductwork or the pressure pushing out against the sides of the ductwork. The velocity pressure is the pressure that's caused by the movement of the air forward as it's being pulled into the ductwork. And the total of those two is the static pressure, and the velocity pressure is the total pressure. Okay, if you imagine it in some ductwork, if we have a device that's sitting in this ductwork and it's measuring, has an opening here, and it's measuring this pressure, well, that pressure is obviously a component that has the velocity pressure. But since the static pressure acts in all directions, including the direction that the velocity pressure is going, right? Well, then it's really measuring the total pressure. If we want to measure the static pressure, we would have to have something that is open to the side of the ductwork. So it's not being influenced by the movement of the air. So that would be our static pressure. And then our velocity pressure would would be determined by taking our total pressure, subtracting our static pressure, leaves us with our velocity pressure, right? Just rearrangement of this formula where this is going over to the other side. Okay, and the third formula that I wanted to make sure we brought up was the relationship between the velocity pressure and the velocity in the ductwork. Okay, so the velocity in the ductwork in feet per minute, right, is equal to 4,005 times the square root of the velocity pressure. Very frequently you'll see that also with the density factor included in that, like that. Okay, if we're working at normal temperatures and pressures, we're probably going to assume that that's equal to 1. And on occasion, very high altitudes and so on and so forth, we might actually incorporate that density factor. But for the most part, we'll be using this formula this way. So the velocity is equal to 4,005 times the square root of the velocity pressure. This number 4,005 is a constant that incorporates a lot of conversions. So in this case, the velocity pressure is in inches of water, and the velocity is in, of course, feet per minute. And that conversion is built into this constant that we have here. So anytime you look at the velocity or you look at the velocity pressure, if you use this formula, that 4,005 is going to relate those two, the inches of water and pressure, to the feet per minute in velocity. If we're working with the metric system, of course, we'll have different measurement. We'll have different quantities for the velocity pressure, different units for the velocity pressure and velocity, for instance, meters per minute, right? But what that'll mean is that we have a different conversion factor. So it's not going to be 4,005. It'll be the same formula, but with a different conversion factor. Okay, but again, we're going to try and stick mostly with English units or U.S. units. Okay, so keep that stuff in mind so that you keep these values within reach. The other thing about these formulas is that very frequently we're going to rearrange them. For instance, if we know what Q is and we know what A is, and we wanted to determine what V is, well, we would then just rearrange this equation to V is equal to Q over A to get velocity. In other words, divide by A on both sides, and that would give us our velocity. In the case of the static pressure, if we were interested in the velocity pressure as we work here, we would just simply move the static pressure over to the other side. So it becomes total pressure minus static pressure. In this case, we can square both sides, right? So if we square the velocity, it's equal to 4,005 squared times the velocity pressure, right? We have to square that also. Square both sides. Okay, then divide by the 4,005 squared. So we can actually isolate the velocity pressure if we know what the velocity is. We can actually calculate it. Very often, instead of doing this, we're going to be using tables and charts to speed up our work, or even spreadsheets, right? So for instance, in this particular case, we might go to our favorite chart number 5A to convert from velocity to velocity pressure, or the other way around, okay, rather than having to do this calculation every time we needed to, and we probably will need to pretty frequently. And remember, stick with chart 5A because chart 5B are the same relationships, but in the metric system. Okay, so I'm going to try and see if I can erase this pretty quickly, all these comments I made here, so I can still use this page to continue with what I want to cover with the answers to these particular problems. Okay, just need another moment here. I should be getting pretty close. Okay, good. So let's take a look at this. First problem is, what is the airflow through a duct of 12 inches by 12 inches with a velocity of 1,000 feet per minute? Okay, and watch the conversion factor. Is actually not much of a conversion factor here, but there is a minor one involved. Okay, so what's that going to be? We know, we just discussed this formula. The quantity of air flowing through is equal to the velocity times the cross-sectional area. Okay, so what do we know here? We know the cross-sectional area, we know the velocity, and we're interested in finding out what Q is. So Q is going to be equal to V, the velocity, and happens to be in 1,000 feet per minute. We know that's the right units per minute, times our cross-sectional area. Now our duct is a square rectangular duct, 12 inches by 12 inches. I'm going to do that conversion right now. Okay, that's 1 foot by 1 foot, so that's 1 square foot. 1 times 1 is 1 foot squared, right? So our quantity of air that's moving through this duct is going to be equal to 1,000 cubic feet per minute. Okay, you can check your units. Feet times feet squared is cubic feet, and minutes over minutes is over minutes. Okay, so that's going to be our answer there. Now notice the closest one is A, because that's unfortunately it was 1,200. I think I tried to make a couple of answers here that might be look reasonable if you forgot to do a conversion. The other way you could have done this is just simply Q is equal to 1,000 feet per minute. Now, if you did 12 feet times 12 feet, you get 144 inches, square inches, right? But then you would have to convert that into square feet, and there's 144 square inches per uh, foot squared, per square foot. So you would have to do that conversion, bring foot square up to the top, and it still come out being 1. Okay, so you can do this conversion before or after. I like doing it before so I don't forget it. What is the airflow through a duct of area 12 inches by 12 inches, right? That's our area is equal to 1 foot squared. Okay, and a velocity of 1,000. Oops, I'm unfortunately, I grabbed that twice. Let's see if I got question number 2 here. Oh, no, I don't. Tell you what, let me go back and get that right now. Okay, and assignment number 1. Okay, question number 2. Let me grab it. Yeah, I think I got enough of it. I'll leave that open in the meantime in case we need to go back there. You can't replace it. Oops. Okay, let me get rid of this one. Okay, back in business. A 2-inch by 5-foot slot hood exhausts air at the rate of 2,000 feet per minute. So we have a velocity, 2,000 feet per minute. We know it's a velocity, not a quantity, because it's feet per minute, not cubic feet per minute. How many pounds of air are exhausted per hour from this hood? And here we've given you the density factor for air weighs 0.075 pounds per cubic foot. Okay, so let's see how much air we have. How much air is exhausted per hour, right? So what we know is we know that we have, oops, there we go. Yep, still have a problem with this. Okay, so I can't get it to right again. Here we go. Good. Okay, so we know, let's see, 2,000 feet per minute. And we want to know how much air is exhausted by this, how much weight of air is exhausted by this, or mass of air is exhausted over a period of how long per minute? How many pounds of air are exhausted per hour? We have it per minute. Let's multiply by 60 minutes per hour. Minutes cancels out, and we wind up with 4 zeros. Right? And 2 is 120,000 cubic feet per minute. Okay, 120,000 cubic feet per minute. Each cubic foot weighs 0.075 pounds. So let's multiply our 120,000 cubic feet per minute, right? And let's see, we have times 0.075 pounds per foot cubed, right? So cubic feet is going to cancel out, and we're going to be left with pounds per hour. Okay, so let's get our calculator out. Times 0.075, and we wind up with 9,000 pounds. So we're talking about a considerable mass of air. And when we say considerable mass of air, where our concern here is that it's going to take energy to move that air. And that air can contain moisture, heat, so on and so forth. We're just taking basic standard temperature and pressure air. And given that density, we might have to include a density correction factor again in some situations. So in this case, we're not going to bother with that. But let's see. I just want to make sure we got that right. 2,000 feet per minute. Let me just go back over this, make sure I got it right. Times 60 minutes is 120,000 times 0.075. I think we got that right. So that should be 9,000 pounds per hour. If I make a math error here, if I make a silly miscalculation, I'm kind of flying without a net here. I'm doing this kind of freehand. So if you see me make an error on here, let me know and I'll go back and correct it. I'll make sure everybody knows about the correction also. Okay, but you've seen me, I do make errors occasionally. Okay, so let's take a look at the next question. 3. At a point upstream from a fan in a duct, the velocity pressure is equal to 3 inches. Now, upstream means before the fan. Downstream would be past the fan, right? So on the upstream side, we expect the velocity pressure to be positive. In fact, on both sides, we'd expect the velocity pressure to be positive because the air is moving in a certain direction through the fan, right? But on the upstream side of the fan, before the fan, we would expect the static pressure to be negative. On the downstream side of the fan, past the fan, we would expect the static pressure to be positive. You can kind of visualize that. Say to yourself, well, on the upstream side, the ductwork is being sucked in because the fan is creating a suction inside that duct, and that's what's getting the air to move. On the discharge side, the air is under pressure and it's pushing it forward from the fan. So that ductwork, if it was a lot of pressure, you'd see it bulge out because it's being pushed outwards. But static pressure in that case is positive. So what is the total? Let's see, static pressure on the upstream side of the fan, the velocity pressure is 3 inches and the static pressure is 3.5 inches. Well, now we know that that's a negative pressure there, right? That's that static pressure being negative 3.5 inches. So our total pressure is going to be equal to our velocity pressure plus our static pressure. So our total pressure is equal to 3 inches of water, right? Plus our static pressure, which is a negative pressure. And so our total pressure is equal to negative 1/2 inch of water. Okay, so keep in mind that the total pressure isn't necessarily a positive number, particularly on the suction side of the fan, okay, on the upstream side of the fan. Okay, and I think we do have a selection there, which looks correct. Okay, so next let's take a look at number 4, which is, let's see what we're doing. Number 4. Number 4 is asking us to do a bunch of calculations now with static pressure, with this formula involving total pressure and static pressure. Okay, I'm going to leave that size, and I'm going to see if I can expand this, make it a little easier to see. Oh, come on. There we go. Okay, so let's take a look at this. So again, our relationship here is our velocity pressure is equal to our static pressure plus our total pressure. Well, in this case, the velocity pressure is 1.5. The static pressure is -3. So our total pressure is going to be equal to 1.5 minus, let's see, well, static pressure is -3, right? We're adding the static pressure, but it's a -3, is equal to -1.5. Again, inches of water. Okay, so this would be 1.5. Okay, so -1.5. Now, next, let's see. We don't know what our velocity pressure is in B, but there's no indication. I think in the problem it tells you that it's a 1 by 1 foot square duct, right, going straight through. It doesn't change size. Well, in that case, the velocity is always the same, so the velocity pressure is always the same. Remember, velocity pressure is related to the actual velocity of the air moving through the ductwork. So B and D are both 1.5. Both of those quantities are 1.5. So if our velocity pressure is 1.5, and in the second location our static pressure is a little lower, well, then our total pressure is going to be equal to, let's see, 1.5 minus our static pressure, which is plus our static pressure, but again, it's a negative number, 2.8, -2.8. So our total pressure there, notice our static pressure is a little bit lower because we've lost energy to friction in the ductwork, right? So that instead is going to be equal to, let's see, the difference there would be 1.3 inches of mercury. And that drop in total pressure is due to the -1.3. That drop is due to the loss in energy, that potential energy that static pressure actually represents. Okay, so that was that one. So now, and finally, we have, this is 1.5 as we've determined already. What is the static pressure equal to? Well, the total pressure is -1.1, and that's equal to, let's see, a velocity pressure, which is 1.5, plus our static pressure, right, which is unknown, which is, let's see, our total pressure, our static pressure is unknown, plus our static pressure. Okay, well, our static pressure, if I move this over to the other side, -1.1, let's say our velocity pressure is plus 1.5. Our total pressure is -1.1. Okay, if I move this over to the other side, it becomes -1.5. So our static pressure in this case is equal to -2.6 inches of water. Okay, so I think that should cover all of that. Sometimes this is counterintuitive, so make sure that you stick with the formula that we were talking about before. If you stick with the formulas and don't let kind of your intuition get in the way of this thing until you get more familiar with these ductwork calculations. Then maybe your intuition will help you. But in the beginning, your intuition sometimes can be a hindrance rather than a help on some of this stuff. So stick with formulas if in the beginning, at least anyway. Okay, so let's take a look at what we have here. The average velocity of air in a duct. Let's see, what is the average velocity of air in a duct when the average velocity pressure is equal to 1.2 inches? Okay, standard temperature and pressure. This little diagram shows a pitot tube inside of the ductwork, measuring the static pressure and measuring the total pressure, and the difference is the velocity pressure. It's a cute little illustration of what this might be. Okay, so in this case, we're measuring, using this device to measure the velocity pressure in inches. Turns out that it's 1.2 inches. So what does that tell us the velocity is in here? So again, here's our formula. Our formula is up here. Our velocity, okay, since we said standard temperature and pressure, we don't have to worry about the correction factor for density. Our velocity is equal to 4,005, right, times the square root of our velocity pressure. I'm ignoring the density correction factor. Okay, so let's see. That's going to be equal to 4,005 times the square root of 1.2. Okay, and again, we can only use, the reason we can use inches of water here, that 1.2, number directly without any other conversions or anything like that to convert it into feet per minute is because the 4005 has the conversion built into it. So let me clear this. 1.2, and the square root of 1.2 is 0.1, I'm going to call it 0.11, equals 4005 times 1.1, okay, round it off, and our velocity is going to be equal to, actually I'll do the calculation without rounding it off. It's equal to 4,387 feet per minute. Okay, I think they guys probably will be able to do that as well. Okay, not too, most of the problem I tried to keep them pretty simple because as we're beginning to learn, we'll learn the basics of this stuff. As we get into actually designing the ductwork, as you've seen already, we're actually winding up to applying some of these principles. Okay, what is the flow rate through the duct if its dimensions are 12 inches by 18 inches? Okay, so now we're being asked a question about, imagine that this is a 12-inch by 18-inch duct. Okay, and then we want to know what the flow rate, how many cubic feet per minute is moving through this ductwork if it's moving at this velocity. Okay, flow rate through the duct. So now, in order to figure that out, there's our second application of one of our primary formulas. Q is equal to the velocity times the cross-sectional area of the ductwork. We know the velocity, we've just calculated it, and we know the cross-sectional area. In a second, at least in a second, we're going to know it. Okay, so Q is going to be equal to the velocity, which is 4387 feet per minute, okay, times the cross-sectional area. Well, it's 12 inches by 18 inches. In other words, 1 foot by 1.5 feet. Since it's rectangular, that would be a height by the width. So that's 1 times 1.5 is 1.5 square feet. Okay, so check our units here, square feet. Check our units here. Our answer is going to wind up being feet cubed per minute, which is what we want for volume. So let's go ahead and calculate that. I'll clear that. And actually, I shouldn't even really clear that. 4387 times 1.5 is equal to 6580. Okay, and I'm going to just call it 6580, a nice round number. Feet cubed per minute. Okay, hopefully you get around the same. If I hadn't erased my final result, which was a little bit more precise than 4387, I might have gotten a number that was just a tiny bit smaller or bigger than 6580. So if your answer is in that ballpark, that'll be swell. Okay, so next, now we're getting into some of the basics. Remember, this homework number 1 is from earlier in the semester. We're getting into some of the basics of dealing with ductwork and devices in the ductwork, transitions, elbows, and so on and so forth. That are going to affect the flow of air through the ductwork. In other words, give us energy losses due to resistance, various kinds of issues with friction, with noise being generated, which is an energy loss, or heat being generated, which is an energy loss as well. So all of those are going to combine into overall losses that are, as we go through these different transitions, whether it's a long run of ductwork, an elbow, a reduction, so on and so forth. Okay, what is a 90-degree elbow loss factor, K elbow, where the elbow radius of a elbow curvature radius is R over D equals 2 in a smooth transition elbow? In other words, not a metal duct, but something that's completely smooth, not something that's a metal duct that is mitered or is a series of partial turns or something like that, or is a mitered end like that, where it's going to have to bend around like that, or even just a slightly tapered duct like something like that, right? Maybe only one sec. So it's not a smooth transition, but instead something like this, where it's a curved transition. This would be typical of, say, PVC pipe exhaust, right? So this could be a large diameter PVC pipe or some other plastic material that's being used as exhaust ductwork, and it's perfectly smooth, and it takes a turn like this. Well, part of what we are interested in here too is not just that this is smooth and that it's a continuous curve and that it's 90 degrees. The other thing we're interested in is how tight a curve it is. So if we're going around the curve, just like in your car, if you're going around the curve that's very smooth like that, that's going to be a lot different than going on a real tight curve like that, right? So a lot more G-forces involved in there, a lot more turbulence in ductwork. So we're going to look at two things. We're going to take a look at the radius of the turn. That's from the center line to the outside, what is the actual radius or center line of the ductwork to the point which would be the center of a circle if you converted that 90-degree turn into a circle. That radius in inches, right, or feet, and we're going to compare that to the diameter of the ductwork itself, right, in inches or feet. Units just have to be the same. So it's a ratio of the radius of the turn to the diameter of the ductwork. In this case, the radius of the turn is to the diameter is equal to 2. So in other words, if the ductwork were 1 foot in diameter, the radius of the turn would be 2 feet. Okay, if the radius of the turn were 4 feet, then the ductwork would have to be a 2 foot diameter ductwork. 24-inch ductwork would be a radius of 4 feet, would give you a R over D of 2 also. So it could be many different size ductwork, but the important part is the relationship between the radius of the turn and the diameter of the ductwork. Remember, this is a radius and this is the diameter. Okay, so let's take a look at that. That's going to be a chart that we're going to have to look that up in. Okay, I have our charts here, and I'm going to see if I can't find our elbow chart quickly, or reasonably quickly. Okay, here we go. I think that's it right there. So our radius to our diameter is equal to 2. And it's a smooth transition ductwork. You can see kind of pictured here. Okay, and our K factor, the factor that represents our frictional loss, is going to be equal to 0.13. Later on, we're also going to see that this is going to be used to calculate the actual loss. This is a constant for the loss here. We're going to take that and multiply it by the velocity pressure to find the actual static pressure that we're going to lose when we go through this transition. The faster the air is moving, the higher the velocity pressure, the more loss we're going to have. This is not going to change. The velocity pressure will change, and that'll make the amount of energy loss that we have to change as well. Okay, so that's what our factor is going to be. It's going to be equal to 0.13. Okay, excuse me. Yep, 0.13. Okay, so let's go on to the next problem. Okay, and let me just pause for a moment because I want to just check, see what's going on here. Hi, George. Take care.
Thank you.
Okay, so this refers to, let's make sure I'm still on recording. I am, okay. Now this problem actually refers back to the previous problem, which involved the elbows. What's the actual static pressure loss, inches of air flowing through a 90-degree smooth elbow with a velocity? This time we have a velocity with a radius to diameter ratio, radius of the curve to diameter of the ductwork of 1.5. Assume standard temperature and pressure, and a density factor equals 1, so we can ignore that. Okay, so we need, in order to calculate the loss here, we need to know the velocity pressure, because our loss, right, the actual loss that we're measuring is going to be equal to, the K, or the loss factor for the elbow, times the velocity pressure. Okay, so it's going to be related to how fast that air is moving through here. So let's see what that loss in static pressure is going to have to be. So we know the velocity, but we don't know the velocity pressure. So we look back here. We have a formula which tells us that our velocity is equal to 4,005 times our velocity pressure, times the square root of our velocity pressure. Okay, so what I'm going to do is I'm going to take our velocity, which we know, 4650, right? And I'm going to move this 4005 over to the other side, okay? And that's going to be equal to the square root of our velocity pressure. So let's see what this comes out to. This comes out to be, okay, remember that 4005 takes care of all of our conversion factors for US units. US units only. Different number for metric units. 4650 divided by 4005 is equal to that number, okay, 1.116. And then now, in order to figure this out, I'm going to square both sides in order to get the velocity pressure. Okay, it's going to be 1.16 squared. Square both sides, wind up with velocity pressure on this side. We wind up with that quantity squared. I'm going to leave this in here, and I'll actually multiply it by itself. Okay, and I think there it is, 1.35, I'll call it. So our velocity pressure is equal to 1.35. And of course, the units are inches of water, okay, because of that conversion factor for the 4005. What's the actual static pressure loss in inches of water of air flowing through a 45-degree smooth elbow at an average velocity of that same amount, 1.5, and so on and so forth? Well, this time it's only a 45-degree elbow. Well, we already looked up for a smooth elbow what the K factor would be. We know what that is, right? And we know that, let's see, our K factor times our velocity pressure. Okay, did I do that before? What's our velocity? Oh, actually, I didn't answer that question yet, did I? I didn't answer the first question, did I? Okay, so let's see. We actually wanted to know what our static pressure loss was going to be there, and our K factor there was 0.13. So our actual loss is going to be K times our velocity pressure, which is equal to 0.13 times our velocity pressure, which is 1.35. And that's going to be our static pressure loss, right? Is equal to that amount. Okay, and what's that equal to? That's going to be equal to K times 0.13. Okay, so our static pressure loss is about, okay, let's see if I got away from there, 0.175. I'm going to call it 0.18 inches of H2O. Okay, inches of water. So I think we're okay there. And number 8. I think so, right? Let's see if I got some other issue there or something like that. Next one is going to be the same kind of problem. Okay, times 0.13. I think it was 0.13. I think that was, yep, 0.13 was our factor. Okay, so next, what is the actual static pressure loss of air flowing through a 45-degree elbow? Well, let's go back to that chart just for the hell of it, right? And our 2, our smooth transition, 0.13. Okay, and in this case, it's still a smooth transition, but it's no longer 90 degrees, right? So I think that we have a little note here. Okay, and let's see if we can find it. For angles different than 90 degrees, let the angle over 90 equal the times K90. In other words, whatever the fraction of the angle compared to 90 degrees is, multiply the K value for the full 90-degree turn. So in this case, it's 45 over 90, or 1/2. So we're going to take half of that 0.13. Oh, I'm sorry, I made a mistake there. It was 1.5. Ah, my goodness. Okay, it's 1.5. Okay, so this should be, I better back up here. Did that affect that? Okay, transition, look at that. The K value here is 0.15. 0.15. K value is 1.5 here, not 1.3. And I'll go back here. And this is going to be, instead of times 0.15, 0.13, it's going to be times 0.13. So let me see if I can recover from this. Where is this? And let's see. I'm going to divide, divide by 0.13. Gets me back here, times 0.15. Should give me about 0.2 of an inch of water. I'm going to call it 0.20 inches of water. This is what happens when you fly without a net. You make mistakes every once in a while. So that's 0.2 of an inch of water for that. And the previous answer was 0.15, not 0.12. I got carried away and went to the 2 instead of the 1.5 ratio. That is actually in the problem. So what's the actual static pressure loss? Air flowing at 45 degrees. Well, instead of 0.15, now we're going to use 0.075. So the velocity is still the same. It's the same problem. So 4650. The velocity is still the same. The velocity pressure is still the same. Okay, and divide by 0.15, get back my velocity pressure. Except this time we're going to multiply it. That's our velocity pressure from the previous problem. This time I'm going to multiply it by 0.075, half of the value that I had before, because that's only a 45-degree turn. And it comes out to about, as expected, about 1/10 of an inch of static pressure, of water static pressure loss. So on that one, our static pressure loss is roughly 0.1 inches of water. Okay, so that's, I think we're okay there. Yes, 0.2. You caught that error I made there, George. You're absolutely right. Okay. So yeah, I don't know. I usually when I make problems up, I usually use a radius of 2, and just out of habit, because I remember the constants. Yes, I don't have to go to the table and look it up. And this problem I use 1.5, and my head was still around 2. Okay, what's the friction loss in K for a galvanized iron duct with the following parameters? The diameter of the duct is 5 inches. The average velocity is equal to 4,000 feet per minute, standard temperature and pressure. Okay, well, what we're looking at here is we're looking at a length of ductwork as air is moving through it. So as air moves through it, we're going to lose energy due to frictional losses. Okay, and the other thing that's mentioned here that's interesting is that it defined the velocity as the average velocity. In fact, we almost always talk about the average velocity. The actual velocity inside of this ductwork varies from the center to closer to the sides of the ductwork because of friction. Okay, in fact, you've seen the gradient in the text that shows the middle of the ductwork has the highest velocity. Okay, so the average velocity is really what we're interested in. The last session, we went through a little bit of a description of how we would measure the average velocity by taking measurements at various depths inside this ductwork and averaging them so we get an average velocity. But all of these equations, for the most part, are based on the average velocity, as if it were a uniform velocity going through the ductwork all the way through. Okay, so it's 5-inch diameter ductwork. The average velocity is 4,000 feet per minute. So we're going to want to look for the average loss, for the frictional loss factor for galvanized iron duct. Doesn't ask us to do any other calculations, just give it the K factor, or the loss per foot in this galvanized iron ductwork. The smoother the ductwork is, the smaller this K factor is. If you have rough or uneven ductwork, even if it's going straight ahead, you're going to lose more energy as it produces more friction. The worst of these are flex duct, which has all those rings and valleys and stuff like that in it. So it's going to have the highest loss factor. Let's go to our table and see if we can't find a description of something that'll tell us what that K value is. Well, first of all, we can go to chart 5, and chart 5 is going to give us that value for galvanized iron ductwork. Now notice this is 5B, so that's going to be metric. This is 5A. Okay, and here we go. And so, for instance, right now, here's our friction loss. That's our K factor. And here is our volume flow rate and our velocity. And you can actually connect the cross-sectional area with the velocity. It'll give you the average flow rate. Okay, that'll give you Q because you know V and you know A. Velocity will give you, if you know the velocity, you can find the velocity pressure on this chart. If you know the velocity pressure, you can find the velocity on this chart. Right now, we're interested in the friction loss. Okay, and this friction loss is for galvanized iron ductwork because it's the most popular ductwork that you're likely to run into. And this is the diameter and the cross-sectional area. It gives you the area by diameter. The area by diameter matched up. The diameter of ductwork matched up to the area that it represents, because so frequently we use round ductwork. Good reason we use round ductwork is round ductwork is the most stable and strongest. If you can imagine, if you have square ductwork for exhaust ductwork, for exhaust ductwork, the pressures, suction pressures, discharge pressures, tend to be higher than they are for air conditioning ductwork. So very frequently on exhaust ductwork, they will use circular duct, where on most HVAC applications, they're using rectangular duct because it's easier to fit into ceiling spaces and so on and so forth. The round ductwork is a little bit more reliable in terms of not collapsing if you're sucking in on it, or expanding, having issues with it popping when it expands as you're pushing high volumes of air through it. So usually you'll see round ductwork in exhaust duct systems. Okay, so let's see where we were again. Now this is for galvanized iron, again, this friction chart, because that's what's used most frequently. Okay, so what's K for 5-inch diameter ductwork? Okay, so we got 5-inch diameter ductwork. Okay, that's going to be here. That's our diameter. And the velocity of air going through here is 4,000 feet per minute. Well, we really would prefer to have the velocity pressure. But to tell you the truth, the way this nomograph is set up, we already know the velocity pressure from the velocity anyway. So let's add a arrow in here. Annotate. And I'm going to add an arrow. Okay, let's take our straight arrow. We'll start at 5 inches diameter ductwork, and we will go up to the velocity of air going through here, which is 4,000 feet per minute. Okay, there's our velocity, and let's see where it crosses this duct frictional loss, or K value. Like it's going through, I would call that roughly about 0.07. Okay, our K factor is roughly 0.07. I think most of you, because it was kind of blasted through, well, actually, I'll call it 0.05. That's the closest major cross section. So I'll call it 0.05. Okay, so our K factor is 0.05 or thereabouts. Okay, not going to make that much difference if you call it 0.06 or 0.07. But our K factor for the ductwork, right, for galvanized iron ductwork, GI ductwork, is going to be equal to 0.05. Right? And what does that mean? That means for every foot of ductwork, we multiply that times the velocity pressure, and that will give us the amount of loss that we have per foot of ductwork that we have. Okay, so now, sometimes you're not going to be working with galvanized iron ductwork, but you can still use this chart. The only thing that you need to do is that instead of just taking this chart at its base value, you have to make a correction for the level of roughness in the ductwork. Sometimes that correction will be greater than 1 when the ductwork is rougher or it gives more friction than galvanized iron ductwork, and sometimes the correction will make this lower if it's smoother than galvanized iron ductwork, such as PVC ductwork. Okay, now let's see if we can't find the roughness correction. See if I can't do it from here. Okay. Maybe I'll do a search. Maybe it's better if I search. Okay, here we go. Friction loss, K times velocity pressure times the length times the right. There's our formula, by the way, for calculating our frictional loss, our loss in static pressure due to our K factor, which is that frictional factor that we just looked up, which was 0.05, times our velocity pressure, times our length of ductwork. Remember, this is per foot of ductwork, times our roughness factor, which will correct for some ductwork that's not galvanized iron, that's rougher or less rough than galvanized iron, and of course our density correction factor, which we can always apply in these formulas. So if we can't come across it, chart number identifies chart number 5. Okay, yeah, that's the correction, chart number 5. See if I can actually find a chart that has it. Oh, here we go. Here's our roughness correction factors. So, let's see, absolute roughness. Okay, let's take a look at average common galvanized iron. Okay, so at most, at 1,000 feet per minute, at 6,000 squeak per minute, all the way across the board, our correction factor is just 1.0. In other words, that correction factor is designed specifically for hot dipped galvanized iron ductwork. Okay, so now if we're using a different kind of ductwork, such as a very smooth PVC pipe, we multiply that K factor by 0.88. In fact, or if we have for in the neighborhood of 1,000 feet per minute, or we multiply it by 0.75 if we're at 6,000 feet per minute. That basically will increase, that will decrease the static pressure loss that you're measuring, that you're estimating in the ductwork, which makes sense because you would expect a lower static pressure loss because this material is very smooth. And of course, the worst case is flex duct. You can see riveted steel or concrete has a very rough surface, so the number is greater than 1. So when you multiply it, it literally doubles the static pressure loss because there's so much friction. And the worst of all is flex duct, which greatly increases the static pressure losses. You'd include that K times R, which is 2.5, times your velocity pressure, times the length of the ductwork, and times your density correction factor if you're using it. Okay, so that's our roughness correction factor. Let me bring this back up here. So the answer to this first part would be 0.05. What is the frictional loss for a length of galvanized iron duct with the following parameters? The diameter is equal to 8 inches. Q is equal to 1,000 cubic feet per minute times, and the length is equal to 43 feet at standard temperature and pressure. Okay, roughness is equal to 1, but we didn't need to be told that because we were told that it's standard galvanized iron ductwork. Okay, so let's see what we need to do here. Well, the diameter is 8. The velocity of air moving through here is 1,000, right? So we need to get our K factor, and then let's see what else we need to do. We need to know what our velocity pressure is as well, don't we? Okay, let's go back to chart 5. Let's see if I can't get to it now. There we go. Okay, whoops, went too far. Here we go, chart 5. Okay, so in this case, in this particular case, our diameter was, so what our diameter was, 8 inches and 1,000 cubic feet per minute. So our ductwork diameter was 8 inches in diameter. Let's pin that there, 8 inches in diameter. He was 1,000. Flow rate is 1,000. So I should have been going through here. 1,000. Ah, here we go. Here's where the issue is. Right here. I went to 4,000 from the previous problem. This problem, we weren't given the velocity. I assumed for a second that it was the same velocity as in the previous problem because I thought I had just pegged one onto the other. But I changed not only the diameter of the ductwork, but I also changed the information about the airflow that I gave you. I told you instead of giving you a velocity like the last problem, I gave you a flow rate, 1,000 cubic feet per minute. So really, we should go through there, pin that there, and continue through, right? So see, if I don't make this line thin, it really makes it hard, doesn't it? Okay, so really our velocity pressure is not 1 inch, but it's 0.6 inches, and that's where the difference is. If we take those numbers, right, and instead of having a velocity pressure of 1, we have, put in also the velocity. Actually, I left out the velocity pressure here. Velocity pressure times the density correction factor. So if I include that, it's going to be 0.03. Actually, that might even change also. No, it looks about the same. That looks right. 0.03 times the roughness factor of 1 times 43 feet times the velocity pressure is 0.6, not 1. Times density correction
That's it.
1. Yeah, that's it. That's so the right answer. The right answer should be 0.03 times 1 times 43 times 0.6. Okay, with, well, now something went wrong again. I know it's not 5.9.
Eh,
0.03 times 43. I'll take that first. Equal to that times 0.6. Okay, which is 0.774, approximately 0.8 inches. Or
right, right.
yeah, and depending on if instead of using the chart, I have, especially with that wide line that I'm using, instead of using the chart, I might have wound up with a little bit more precise number than this if I had done the calculations using the velocity and pressure formula and so on. So, but you could do it either way. And this is, in general, that chart is good enough. Remember, all of this is an estimate of what the final performance of the
Yes.
is going to be. And we're going to build in some level of safety factor when we're doing all this. In fact, when we did the band calculations, we actually saw we added in a correction factor of about 30% or something like that to the fan. Okay, so I'm going to call it for now. I'm going to record my calculations for assignment 2 and assignment 3. I'll post this one and assignment 2 tonight, and then I'll wait until tomorrow tomorrow night to post the last assignment, so at least people can get a look at it before. I made the due date for the assignment 3 tomorrow night since several people hadn't submitted it yet. All right, so I appreciate the help. So otherwise I definitely wouldn't have caught all these errors before I put it up. I probably wouldn't have checked my.
No problem.
Okay, so have a good afternoon.